reason besides it's just the way it is for why for level 9, I think, when you pass in a null pointer for RB, there's a null in the first part of the array, it just goes straight to the environment when it's indexing RB.
Assembly, I guess.
Why is it going to environment? Because that just happens to be where the environment's set up.
But like if you're passing in RB and you just have the first index is null, and then you have actual values in the following indexes, it seems to just immediately skip over that and go straight to the environment.
But the other levels that doesn't.
If you go like RB 1, 2, 3, 4, it'll index into the environment array, right?
Right.
Because that array happens to sit right after the RB array.
Yeah, but that's even if you pass in if you try to pass in stuff after the null pointer, the RB array.
Right, because there's no like bounds checking that says like if that's a 0, then don't index past it. It just blindly does the math. That's just C, you know.
I don't know.
Double check, make sure that it's valid. And there's no guarantee that the RB, the NV array is going to be out there, and the P array is going to be out there. It just happens to be the way the compiler set it up, and so you figure that out and go, oh, I can get to it that way. But it could have been elsewhere.
I guess I was just surprised that even if you try and pass stuff in through RB after your first null pointer, whatever, it just skips that as soon as it sees the first null pointer and goes straight to reading in.
I'm not sure what you're saying. Right, so there's two ways to set argv to null, right? One is you can set argv to null.
Yeah.
And the other is you can set it to a non-null value, but then in the list, the first pointer is null.
Right. Yeah. And so in the list, if you pass in null and then things afterwards in that list.
You're surprised that all gets copied?
No, it just skips it.
What do you mean skips it?
Like, at least when I passed in stuff after the first null index, it skipped that and went straight to my environment variables when it was getting in and stuff.
I mean, when you pass in an array of pointers, if there's a null, I'm not sure what happens after that is even defined, whether it copies it or whether it skips it, as you say.
Yeah.
So, okay. Oh, am I getting some policy agreement here? All right. So let's see. It's November now. We have a month and maybe a week or two left in the class. And last time I sort of went through the the format string stuff. And I abbreviated the end portion of it because we were running out of time, and I just wanted to show you that what the final form of it looks like. I want to do this again a little more slowly and explain how it works step by step and some of the tricks that you can use to calculate offsets and so forth, rather than just, last time I threw up the answer and I went, look, it works, magic, go by. Right? So this time we'll actually derive some of the steps. I think it won't take the whole hour since we've done most of the work last time talking about the background stuff. Then I have some more stuff to talk about, wrap up the whole Razor exercise set, and then we'll move on to web-based stuff, which will feel like complete topic whiplash because we're going to go from the deepest, most intimate flags within the registers to all of a sudden the web, which feels very high level in comparison. Okay? Any questions or anything? So the way the rest of the class will run is today's the 4th, 5th, and we've got homework due, the last 5 levels, in a week and 2 days, which will bring us to 14. And then I'll assign the first 5 levels of Blade, which is the next machine, and that'll span over the Thanksgiving break, the fall break. And then we'll do the last 5 levels after that, and that'll bring us probably up to the last day of class. And then we have a final, I think, on a Saturday. Yeah. This on the 14th at 1:30, and that'll be in this room. And so prior to that, we're going to make up teams, which is mandatory for the final because I don't have enough machines. And then unlike Razor and Blade, where there's a single VM for all of you, each team will have a separate VM. And that way there won't be any chance of crosstalk or because in the final, a lot of times you'll be actually messing up the machine, disturbing its environment in order to break certain parts of it. And then I don't want that to affect other teams. So we'll each have a separate box just for the duration of the final. And the goal of the final would be you don't have an account on the machine, unlike all Razor and Blade where you have accounts. Here you won't have an account on the machine, you'll just have an IP address, and it's going to have a web server running on it, and you need to get root on that machine. So all the way from opening index.html down to root is the challenge, and you've got 2.5 hours. So that's a ways off yet. That'll end the course. Okay, any questions about it?
How are the groups going to be just random?
Yeah, so groups will be formed either, there are 2 phases. The first phase is you find a group by talking to people you know, or cold calling people in the class. Hey, I'm Curry, want to be on my team? And if that doesn't work and people are still singletons, then I'll force marriage you guys at the end. And I have a good idea of how people are doing in the class. I've been watching, of course, the Razor leveling, and I'll see on Blade how you're leveling, and I'll know who's having more trouble and less trouble, and I'll try to make teams that are balanced in that respect. But usually in this class, people make their own teams. Usually I don't have to do too much at the end of making teams by force. Anything else? All right, so back to this mess, the format string stuff. I was, last time, working on this machine, this vulnerable program. Wireless working? I wonder if there's like a captive portal, but I just had to re-authenticate. Seems to work. Is Razor down? Is anybody on Razor?
I'm on Razor.
You're on?
Yeah, it seems fine.
I don't know. I've never seen communication prohibited by filter before for pings. Okay, that works. I don't know what's going on with Razor. What is that? Communication prohibited by filter. Gateway. 10. Last time I had a problem like this, it was some really dumb thing. Like I was on a different machine and didn't realize it or something. I'll take this down, back up.
Oh, you're on the guest Wi-Fi.
I was on guest.
Yeah, I think so.
Wonder why I would choose that one. Been on wireless forever. No, you're right.
Yeah.
There we go. Thank you. All right. Let's see. We were looking at this program. Which is about as simple a format string exploit as possible. And last time I spat out some like long printf with a bunch of %x's and %n's and \x this and that and so forth, and it worked. So I want to go through that again and go through it more slowly and sort of piece together the solution rather than just spitting it out. So last time it was a string kind of like this that worked. And the idea was, there's an address here. It's in little endian format, as it needs to be. And there's an address here. And these two are 16 bits apart. This is the low 2 bytes of where I'm trying to write some number. And this is the high address of the higher 2 bytes where I'm trying to write a second separate number. And what's the address, what's the value I'm trying to write to these addresses?
Return address.
No. The value.
You're trying to
Address of my
override.
shellcode,
Yeah.
right? So the structure of the attack was like this. We've got stack. We've got saved, frame pointer. This is in main. This is the return address, which in main, when main ends, it goes back to the cleanup code that from init, the C library. Then there's argc, and argv, and np. And then who knows what else? Maybe the argv array of pointers, terminated, and eventually you get down to the environment, which is going to be a bunch of null terminated strings that has key equals value, key equals value, key equals value, all null terminated. And that's going to be down here. Probably before that, let's see. I'm going to make this up. I don't know exactly where it is, but let's say argv is like this. So argv is a pointer to an array of pointers, and the first pointer is going to be what? argv 0, which will be quote dot slash format. Null terminated, that's why I'm putting double quotes. Then the next argv slot will be whatever argv1 was, and that I get to set. So this is going to be backslash x d0 backslash x cd backslash x ff, followed by percent something x, followed by percent something n. But this is my attack. And then what's this third slot in argv? Nulls, right? The null pointer, 4 bytes of zeros, and that ends argv. NP will similarly be an array of pointers, which, and I don't know, maybe this array of pointers is above here, down here, doesn't matter. But what is important is that argv1 is somewhere on the stack. Why is that important? Because you want to be able to use a parameter selector to find it. So it has to be in a positive direction from the top of the stack, because printf, when it wakes up, is going to look at, this is the top of the stack, and these are my parameters. And there are no parameters, right? Because argv1, well, yeah. There are no parameters that feed into this %x and so forth that were pushed on stack, because there's only a single parameter available. Okay, so this is the top of the stack. Stack pointer's up here. We need to be able to use a parameter selector to look down and find these addresses. If these addresses were in a variable, let's say in a global, where would they be in memory?
Higher.
Up here in the data set. And what parameter selector would get to them? None, because you can't put negative parameter selection. Okay, so we need these addresses to be somewhere in available memory so that we can reference them with a %n. We can find them by saying $, the proper number offset to find them, so that the %n will use these as places to write to. What are these addresses? What are they pointing at? The low word and the high word of the return address of this, right? Okay. If I didn't have access to argv1, could I put this in an environment variable instead?
Yes.
Yeah.
Yeah, it would be down here. It would be a little lower down. My parameter selector would be a bigger number, but I'd have to reach further down into memory. But I could. Now, I can't do that over a network connection because I don't have access to the environment. I can't set variables. So maybe I'd have to push it across in an argument. All right. So for this exploit to work, I need, and I wrote this last time, 3 things. 1, I need to know this, right? The address of the return address. And when printf actually does the write, W-R-I-T-E, the write thing, in other words, when it executes this %n, that's when it's actually overriding the return address with the address of the shellcode. I can overwrite this guy, but there's going to be 2 more activation frames at the time that this happened. There's going to be printf's activation frame itself, because that's a function. So it's got its own, move the frame pointer, push the return address. That whole frame is going to be, activation frame is going to be created. And then there's vprintf, which is another one within printf that we'll see in a minute. It's got an activation frame. So I could corrupt vprintf, or I could corrupt printf, or I could corrupt main. Any of those return addresses, because they're all going to be followed on returns. And anywhere I want, I can plug in and jump to my shellcode. And I'm choosing this one because it's easy to find, but I could have chosen any of the other 2. It turns out I'm going to leave the other 2 untouched. Let it return, and then when this returns, then I win. It may be the case that when main comes back from printf, it does more stuff that somehow depends on this being intact, and then I'd have to corrupt these other ones to commandeer control earlier. But it turns out it doesn't matter here, and it won't in level 12 either. So I'm going to get this one, and that means I need its address on the stack. Number 2, I need the offset to argv1, because that's where these addresses are. And when I say offset, I need how many 4-byte slots down the stack do I need to look? From top of stack. That's not an address, that's a number, an integer. And then 3, what's the last one? The address of my shellcode. And I've decided to put shellcode in the environment, so that'll be down here somewhere. So what I want to do is I want to create this guy such that when the printf's %n works, when it executes the %n steps, it looks at this address, and then it writes the value of the address of my shellcode. I'm going to have to do 2 separate steps, 1/2 and then the other. The address of shellcode on top of this guy. Right? So I have to look down to find this thing, and then I have to write the correct value, which is this address, into the right place, which is at this point. All right? So now let's go and derive these 3 things. Any questions? You understand how it works? All right. And it is possible, by the way, instead of doing 2 16-bit writes, I could do 4 separate writes. So this is 2 writes because I'm going to write 2 bytes of this and then 2 more bytes of this, and I got 4 bytes. But I could, if I wanted to, have 4 different %ns, and I could write a byte at a time. Maybe like I could write a B0 follow what this is. Say I want to write FF 9D B0. I could write B0 then 9D then FF then FF. How would I do that? what part of my printf format string decides what value I'm writing? How many characters have been output thus far? That's what %n cares about, right? So if I want to write this value, I've got to have B0, whatever that turns into, 11 times 16, 176, right? 176 characters have to be output, and then I'm going to use a %n and write this value. And then this is smaller. And you can't un-output characters to decrease the value that %n is going to put out. Well, maybe I could write this one, then these two, by going in different orders, right? Because I just have to have my addresses be in different orders. Or maybe I could write B0, and then I could write a higher number, 19D, which is bigger than B0. And then that 1 will get overwritten, and then I'll write 1FF that way. I could do it that way. But the problem with doing 4 writes, there is no problem really. It's just that it's more stuff to get wrong, more opportunities to get stuff wrong. If I can do it 2 at a time, I only have 2% ends that have to be correct. So I prefer that.
And
All right.
at least for the sake of what we're doing, it's more than likely always going to be FFFF.
Almost certainly.
So we could even just do 1, right?
How so?
Like we only overwrite those 2 lower bytes. We don't even bother overwriting the FFFF because that's going to be the same anyways.
I'm not following you.
So like if we're writing, like say we're doing, instead of writing 4 times, we're writing 2 times, right?
Yeah.
But one of those writes is just writing FFFF over something that already is FFFF.
So I could do a 32-bit write to start with, because I'm just going to overwrite the FF.
His point is the original return address mostly should start with FFFF.
Oh, I see.
Very likely will, yeah. And the return address that we want to overwrite it with also is going to start with FFFF.
So I could just actually leave the FF in place and do a single 16-bit write.
Yeah, that's what I was, yeah. In theory, right?
Yeah. Yeah, so I mean, normally these return addresses, like if we looked at these higher frames, they're going to be in the text segment. And those are not going to start with FFFF. But it happens that this one will, because it's returning to the kernel code or the libc code it does start with FFFF. So it does work in this case. And you can get away with a single 16-bit write.
Right.
That's true. All right. So this is the form of the final thing that works. Let's go actually work it out. So I guess let's put some crap values in to start with. As I said last time, you want to make sure that stuff is about the right size, because every time you change the size, everything's going to get messed up. So is that 8 bytes? So I'll just put in filler values. And then we know we need to put in some space for %x. That's going to determine the value that we write to this bad address, FFFF. And then there's going to be parameter selection, and I'm going to do 16-bit write. We could just do just 16 bits, like you suggested. Maybe let's do it that way and see if we can get it to work that way. That means we're done, doesn't it? So I'm going to do as Alex suggested, that we're only going to write the low 16 bits. And in fact, to write the low, we even need the second address. I've never tried this before, but it should work if the return address, which we'll go check in a minute to see if it's going to work. I'm missing an opening quote, looks like. And then I need a close single. Does that look right? I mean, it's not right, of course, but at least it's free of syntax errors.
Yep.
Okay. So What's that? What's the seg fault? What's happening?
Can we not, are we not allowed, like, if we're writing to that memory location, does that cause an issue?
We don't know what are the 100 parameter selections, so we overrode that most likely.
So I just put in a bunch of random numbers, not random, arbitrary numbers, right? So what happened here? Printf saw 4 of these bytes and printed them. It saw this. Is this causing a seg fault? %12345x?
No.
No, that's just reading whatever happens to be on the stack, which is going to be some value, and printing it in a 12,345 width field in hex. That's fine. But this is the problem, isn't it? This is saying, look 132-bit slots down the stack, find whatever pointer is there, and then write 1, 2, 3, 4, 9. Write that value to that pointer, and that pointer is almost certainly going to be invalid. So it's going to try to write the number 12,349 to whatever value it found at 100 slots down. And that's going to seg fault. Now, the seg fault that you get is in this, it's in actually a subroutine. Oh no, it's in VF-printf. Remember I told you printf is going to call another subroutine called VF-printf. This is BT, which stands for backtrace. And what's this doing?
It's printing the function on the activation record and the reverse order.
Right, so it's showing me all the activation records from the current place and then all the enveloping, all the enclosing activation records that are above it, right? So we've got main, which called printf, printf called VF-printf, and VF-printf has this instruction, this calls the fault. Printf is extremely complicated. It's not part of the kernel, and it's not a part of what you wrote in your code. It's part of the C library that gets packaged in automatically for free every time you compile a C program. The offending instruction, we can look at it with this. It's move the BX, how many bits is BX? 16-bit register, right? EBX is the full 32. BX is the low 16 bits. Why is it only writing 16 bits?
Because of HN.
HN, we're doing a half word write, right? And then EAX with parentheses means go to the address that's indicated by the value of the EAX register, right? Without the parentheses, this would be move it into the register. With the parentheses means the register has an address, move it to memory indicated by the address in the EAX. So it's trying to write to address 31 decimal 1F hex. That's invalid. Can't write to the first page of memory. All right, so what's happening is that this instruction is attempting to execute pay dirt, the actual write of the HN, %HN, right? At some point, that %HN is going to involve writing to memory, and when it attempted to write to memory, that's when it blew up. Makes sense. In fact, this is the instruction that's always going to blow up every time your exploit doesn't work. And the handy thing to look at, usually BX will be the value you expect it to be. What determines what's in the BX? What about this is going to determine what's in the BX register?
The number of characters printed.
Right, it's going to be the number of characters thus far, which the first 4 will be pretty much fixed at 4, but this number you set. And as you tune that number, what's in the BX is going to change. Okay? What is changing what's in the EAX?
The parameter.
These guys, right? Not only what these guys are set to, but also making sure that your parameter selector is getting you to the place where these guys live. So these two things you're going to have to tune. Most likely it's going to be this value that you're going to be playing with, not only to find the right depth into the stack to find the FFFFs, but also maybe adding some stuff at the end to get the alignment to work out right too, because it won't be on a 4 byte multiple. All right. So let's start chipping away at getting this to work. So the first thing I'd like to do is try to figure out how to get this parameter selector correct. 100 is clearly not right. I wanted this to be FF, and it turned out to be 1F. So I'm in the wrong place. So what depth do I need to look at? I'm going to go and disassemble main. And why when I say disass does it say no function contains the program counter? I'm in some inner frame, inner activation record, so I could type up, right? Do you know that? Up means go up one level in the activation records on the stack. So now I'm at vprintf, and I can even see the call to the function that caused the seg fault. Now the problem with disassemble is it will always start at the top of the function. And it may be 30,000 instructions down that I care about, right? So I have to do this for a while. And I'm looking for a little arrow on the left side that shows, there it is. So that's where I'm going to return to. That means this is the call that went to the subroutine that did the move that caused the seg fault. If I go up another one, now I'm in printf itself. And when I disassemble, it's going to start at the top. But it turns out printf is a really short function. It just calls vprintf. Up one more time, I'm in main. And unsurprisingly, in main, I just called printf, and I'm returning to add4. What's add4 to the ESP? What's that doing? Yeah, it's cleaning up the stack, right? There's a parameter on stack that was pushed, which is my argv1, and this is cleaning it up. Okay, so I'm going to rerun this program, and I'm going to put a break right here at the call to printf. And you know you need an asterisk, right? All right, so let's rerun this program and look at what happens just as we're about to call. That's not the right thing. That's the right thing. Okay, so we're now about to call the printf, and I want to know how many 4-byte slots down the stack do I need to look to find my FFFFFFF? Let's see. So how do I do that? How far down is it?
Check a ESP.
Check the ESP? Okay, so ESP is the value currently at the top of the stack, right? That's it. And what I want to know is what's the distance to here? I think I have it in the slide too. Yeah. What's on the top of the stack right now?
The arguments passed to main.
Huh?
Yes.
What's right here?
The arguments passed to printer.
The argument that's going to be passed. And what argument is going to be passed?
The string, also the address of what you want to print.
Okay, now what is that?
That's done.
argv1. Not argv and not the slot here, but actually the string. The address of this has been pushed here. So there's a pointer to that string. How did that get there? There's a push, right?
Yeah.
That's because in our source code, it said printf argv1. That's the parameter. Pushes parameters right to left. There's only one. So it pushes argv1. So whatever, I can just look at the top of the stack here to see the address down here and then do the math. This address minus that address over 4. Now it may not be a perfect multiple of 4, so we'll take a look. So if I say print, you need $sign to treat registers as variables in GDB? I don't know why. So ESP is currently this. And then, is this going to work? It doesn't want me to do that, so I have to cast it. Oops, I have the dollar sign in the wrong place. Oh, let's do it in hex. Okay. So unfortunately, I couldn't just say star ESP. I had to tell it it's a pointer to an integer and then dereference it. But this is the value at the top of the stack. Another way to see it would just be examine memory.
x/x.
Gives me the same value, doesn't it? All right. So that is here. Was it D806? Which means that this address here is that FFFF D806. That's the address on stack here. So I need to know how far it is from here to here. And then divide that by 4, and that'll be how many parameter selectors down. And that's going to be a fairly stable number. It's not going to move around for us too much. At least if I don't change the size of my printf, my argv1. Okay, so let's do that math. So the distance, I want it in decimal, I guess, is what? It's the second number minus the first number. So I want the number I just produced, that thing, and then I want to subtract the current value of ESP, and I want to divide by 4. And before I divide by 4, I'm going to see if it's even a multiple of 4. What did I do wrong? What am I doing wrong? Thought that would. Oh, it's because this thing's not an integer. Okay, so 498, is that a multiple of 4? It's not, right? It's 2 mod 4. So that means we're going to, unfortunately, be off by a couple. All right, so divided by 4, I'm 124 slots. So if I tell printf to look down 124, it should get me kind of around here. I might be off by a couple because it doesn't look like it's a perfect multiple of 4. I'm going to have to jiggle it around a little bit, but 124 is ballpark. Okay, so that's one of our numbers, about 124. All right, what else do I need? I need to know the address of the return address. Let's see where that is. Looks like it's right here. And what's that address? Looks like it's 4F's D61C. Now that might move around. I'll use core dumps to get the exact number in case it's moving. GDB's showing it to be slightly different, but looks like it's about FFFF D61C. That, we don't have a no-op sled or any help or wiggling room or approximation techniques. We have to get that one on the nose, unfortunately. Okay, and we have to get the offset on the nose. Address of shellcode, that can move around a little bit because we're going to have a no-op sled. All right. Address of shellcode, let me go put shellcode in the environment. For the couple of you who've done level 12, is that what you did, shellcode in the environment? Hamza, Chance?
I actually put it in the second argument.
Oh, you put it in RV2?
Yeah.
That'll work too. That just means that it's going to be right here instead of down here. But you can also put a big sled on RV2. Okay. So let's go put the shellcode in the environment.
I don't think we're going to be able to do a single 16-bit right here, though.
Why is
The
that?
Return address isn't starting with that.
Oh, you're right.
Yeah, so we're going to have to do 2 separate writes.
Wait.
The
Yeah.
location of the return address
That's
does,
it.
but the return address itself doesn't. So.
Yeah. So we're going to have to overwrite this.
Yeah.
In level 12, did you have to?
Yep.
Had to as well. Okay. let's go back to the other format then. We're gonna have to do two 16-bit writes. But let's go put shellcode in our environment. Do I have it already in my environment from last time? I don't see it. Anybody see SC equals? No, it's not there. So let's go set it. What do I type? Export. Don't forget to export. You'll have a very bad week. That's how long you'll spend for trying to figure out what happened to your shellcode. Is about a week. Okay. So do I have shellcode now? There it is. And this is just going to run a shell. It's not going to run lead. And that's going to move everything around, right? Now, the offset might be okay, but the return address is probably going to be different now. So I think I'm gonna move right to core dumps. And undoubtedly going to screw this up, so help me. Let's see. I'll go ahead and put in the address of the return address as we found it, but it's almost certainly going to be wrong. So what do I write here? We're going to go back to two 16-bit writes. So should I write the low half of my shellcode address or my high half first? Low half first. Because that's going to be the lower number. The higher number is going to be FFFF. And I want to save that for the second part.
It won't matter because you can just change your parameter.
I can change the parameter selector too. That's true. I think it maybe intuitively makes sense to do the low half first though. Okay, so what's the low half?
1C.
It's going to be that, right? And we'll add 2 to do the upper 2 bytes. So I'm going to, and I have to do it backwards for Little Endian. So is it 1CD6 up there? And then I'm going to do the upper half, right? 1E. I'm relying on people to yell out and say, no, you missed something. Go back. Everyone's shy. Or imperfect. One of those two things is happening. Okay, I think it was 5 digits is probably going to be, we might have to fix that if it's not 5 digits. Okay, so we're going to get 8 for those 8 bytes, plus that number, 1, 2, 3, 4, 5. And then we're going to do a write. And this is going to be 124, we decided, which is not going to be right, probably, but whatever. And then we're going to put another spacer. And I don't know, we need to get from there to 65535, which is maybe 4 digits. We might have to fix this. And then another write. And that's going to be 125. This second one will always be one more than the first one, unless we're doing them in the other order. So if you get 124 correct, then the next number will be 125, because that'll be the next parameter, which will be this one. Is that it? Looks good? Okay, so I'm going to go right into core dump mode now, and I'm going to try to correct these values and find my shellcode and all that. So let's go back into GDB. Are there questions? Is everybody with me? All right. Okay. What's the instruction that segfaulted if I look?
EIP.
EIP. But what is the instruction? Move EX to parenthesis EAX, right? It's writing 1, 2, 3, 5, 3. Explain that.
Because we have the 8 bytes that we're writing first, and then we're writing.
1, 2, 3, 4, 5.
Yeah.
And what's 1, 2, 3, 4, 5 plus 8? That number. Okay, so no surprise, it's writing 1, 2, 3, 4, 5 plus 8. Now, the problem that segfault is it's writing it to some crap place that doesn't make any sense, right? It's writing it to this. Now, this looks suspiciously like ASCII, doesn't it?
Yeah.
25 is a percent. That's the digit 1, that's the digit 2, and that's the digit 4.
So you overshot.
I overshot. So if we go look at, I'm going to Control Z out and just look at what our string was. I hit %124. It looks like I hit this. So when I reached down the stack to try to find my address, I reached too deep, and I went over into my format string, and I was looking at %124 as an address, which of course turns into the address 3/4, something you can't write to. That's what segfaulted. So one thing I need to do to fix this is I need to decrease the highlighted number to go a little more shallow, so that I only go to here, right? And that looks like it's going to be about, I don't know, 1, 2, 3, 4, maybe 4 fewer, about a 120-ish. The other thing I might as well do while I'm at it, while I'm here, is figure out where my shellcode is. So how am I going to find my shellcode? I could be smart or I could be dumb. Let's see, which should I? I could follow like environment pointers or something. Or I could just start dumping memory until I see it. There's our V. You can start looking there, I guess. It's going to come after that. All right, maybe I'll go and look at our MP. So MP is there, meaning the array of pointers is there. So when I look there, these are all pointers to strings. So the first environment variable is at that memory address. So maybe I'll start looking at these as strings. So there's some of them. You see SC? There it is. So there's the address of my shellcode. And of course, 220 is 90 hex, but it's in what format? Octal. Welcome to octal. That's a no-op in octal. Thank you, GDB. 197 of them, apparently. I don't know why it decides 197 and then 200 more and 200 more. I have a 1024 byte sled, minus the size of my shellcode. So I have about 1,000 of these, which is why you see 200, 200, 200, and finally my shellcode starts here. So let's aim for the middle of this thing. Somewhere around there. Looks like about the middle. So I'm going to say DC80. And I can be pretty far off and it'll still work. All right. And that won't move too much. It's in high memory, it's in my environment, it's way down this picture on the bottom. It's not as susceptible to perturbation when I change things. And even if it's perturbed a little bit, we're okay because of the sled. So that's the good news. Okay. What else do I need? I need this to be correct. As we said, we're going to have to lower it, looks like. And then this has probably changed. So let's go figure out the exact place that the return address is. We're looking forensic return address at the core dump. This is much better than looking in GDB where things tend to be different from the live version. And people notice that GDBing the live homework exercise isn't allowed, or it will drop privileges, right? So you can just make a copy of the binary. I know some people did that. Okay, so let's go find out where the actual return address lives. Which should I look at?
EBP.
Which should I look at?
Just EBP.
EBP. Now, this EBP is correct. It is showing me mains activation frame, but that's only because I went up, 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 right? If I went back down,
Yeah.
And then I look at EBP. I'm looking now at the activation frame of this thing within vprintf. That's not what I care about. I mean, you could overwrite this one instead. It'll work because it's going to return 2. But if you want to target main, I type up 3. That'll pop me up 3. I don't have to type up. If this is the one you want, go up to main's activation frame and then print out, and then you should be in familiar territory. You'll like recognize argc sitting there. And this is argv. And this is the one we want, right? So that's 4 more. That's this address, D22C, which is different, yeah?
Yeah.
And that should be consistent because ASLR is off. That should always be the same every time you run this format victim. Cool. All right, so we got that. Now we need to know, that's the value we're writing, right? So we need to know what this is in decimal, yeah? Because we're using percent blah x. And we need those numbers to be in decimal. So let's print these out in decimal. $53,804. And then we're going to subtract what from this?
8.
8, because we're going to have 8 already from this stuff will cause 8 more. And then I need the offset from here to 65535, yeah? Do I subtract 8 here or not?
Yeah.
Yes. Yeah.
Everybody's saying yes.
Not
My brain is
right.
saying no. Who's
This-
right?
This is already, like after you print it, it's already there. So
It's already
8
there,
has
so
already
you-
been counted.
So I don't need 8, right? I don't need to subtract 8 more. 11, right? Because the 8's already going to be baked into the 50. We're going to write 5308. That already counts the 8. So I don't want to count it a second time to get the next offset. 11,731, which means my 4-digit guess is wrong. We'll have to fix that. So let's go fix that. Man, when you change the width on this stuff, everything blows up and you have to start over. I just changed the width. Why? Because I only get allocated 4 characters right here. 1, 2, 3, 4. It's going to be 5-character offset. 11,731. All right, so let's go and try to patch this up. It's still not going to work, but we'll get closer to the answer. So what's the first address? Is that right? This will be 2 bytes higher. Is that right? This is going to be what? 53804.
9.
And then I have to subtract 8, so it's 76. No, 96. 796. And this we thought was about 120. We have to probably fix that. This is going to be, what was it, 11 something?
11731.
731. And this is 121, one after this. Okay. So let's go take a look at the world now. I don't know. Let's take a look at where it's trying to write to. I'm not even going to look at the instruction. I know what the instruction is. It's move bx parent eax. So I'm not going to look at it. I'm just going to look at my ex and see where it is I'm trying to write to. A 2. That's fun. Okay. Let's go see if my shellcode's at least in the right place. What did I say my shellcode was? DC80? At least I've got the no obsolete there, so that seems like it's in the right place. What about the address of the return address? Let's see what that looks like. So I'm going to go up 3 into main, and then is it D22C?
Yeah.
So that's holding stable. That's good. So it looks like my parameter selector is the thing that's really off. It's not getting me the right address.
Oh, 2 could be argsy.
That'll be really weird. That means my parameter selector is only like 3 or something instead of 120 something. Now there must be a 2 that's way down.
Maybe.
And you know, honestly, what I'd be tempted to do here, instead of thinking, would be to just change it to another number till I get something I recognize. I'm gonna just change it a little higher. You know, it doesn't cost you anything to mess with stuff and look around until some things get easy. And this is a really, what? I guess maybe my 2 moved from 1% in to the other percent in. It's like faulted in a different place now. All right, I'm gonna just keep using the caveman method here and going down deeper. Eventually, I'm gonna hit my string. It took me a while to just come to terms with the fact that I can just poke around with this. It takes literally 3 commands to move something and try again. So I'll just keep poking around till I see something I recognize. This is %537.
537. Yeah.
%537. So where am I?
Oh, you're catching the 122s. Yeah.
So why was I getting 2 before? That's really weird. %537, that's what I just saw, right? I don't know if that was my first percent in or my second one. But that's disconcerting. Where was it getting 0002?
Let me check EIP.
Huh. To see if it was even the instruction we think it was? Okay, let's do that. I'm going to change this back to 120121. And then, yeah, it is where I think it should be. But why is it, was he getting a 2? This has never happened before. That works. And how is that different? D22C, D22E is the same numbers as we've been using. The rest of the shellcode's a little different.
That's quite a bit lower.
Quite a bit, right? Yeah, it's hugely lower. The parameter selector is the
Or
same.
sorry, quite a bit higher. No.
This
We
is
had-
higher?
Yeah, we had
56?
53, 804 before, and now we're at 56. So it's about,
That's a huge amount different.
yeah.
The parameters are selectors. I don't get that. Unless I've got some weird syntax error in this one. D22C, D22E. That's the only thing that's different is the %X's, yeah? Everything else is the same? Okay, so here are the 2 things.
The
One-
dollar sign, you're missing a dollar sign before your second name.
Oh, there. So that is just, it is argc. Because of no dollar sign, it's just pulling it off the stack below, and it is argc that's being used as an address. That's the problem. Thank you, Alex. Okay. My mind was almost gone there. Okay, well, that's the correct address, right? Oh, no, it's not, it's off slightly. Yeah, okay, so I want to write to FFFF D2 2E, but the D2 is up here and that's in the wrong place. I want to shift everything left by a byte. So one thing you can do when this is happening is, did I have an extra X on the other one? I didn't. Is you can purposely pad something out. So if I put just an extra character, it'll shift everything down lower in memory. So what happens now? It went the wrong way. I'm trying to get the FFs to go to the left. So maybe if I add 2 more, if I add 2 more, okay, so that's %537. It's probably my second percent in, the first one's working. So now what I need to do is decrease all of these. Did I just mess up?
$.
Yeah, dollars are second.
Thank you. Illegal instruction, that's new. It's trying to execute a period.
No, it's come out of printf. It's not in printf anymore.
You're right. So it's jumping to the wrong place
Yes.
for shellcode. D22E was shellcode.
Why is
No, shellcode was DC80.
yeah?
Yeah. It's,
Oh, shouldn't we be writing the address of the shellcode rather than the address of the return address? 53804 is.
Oh, yeah.
oh gosh, you're right. Yeah, no wonder our %X's were so big. Okay, we have 6 minutes. Let's fix this. So, address of the shellcode. I couldn't. You see what I did wrong? I converted the wrong number to decimal. This number should be converted to decimal. I'm writing the wrong thing, which is why it's so different from the exploit that I had that worked. So that's a huge mistake. Erase that and start over. This should go to decimal. Okay, so let's go do that, and then it'll work, I think. Sorry about that.
That's
That's a bad mistake.
56448, by the way. Just
So
to
what?
speed things up, it's 56448.
56448?
Yeah.
56448. And we're going to be subtracting 8, and then what's 65535 minus that?
What was it again?
65535 minus 56448.
65535 minus 56448. That would be 9,087.
9087?
4 digit again.
4 digits again? Thank you for screwing that up too. That's a big mistake, really using the wrong address, because getting this right is hard, and then having a teacher who's saying the wrong thing just makes you more confused. 56448 minus 8, right? And then this one, 9087. I'm going to take the X's off the end, they're already gone.
21.
120, 121, might as well, since I took the X's off. And it works. Helps if you write the address of the return of the shellcode and not the address of the return address. I don't know why I converted the other number. It's completely wrong. Okay. Clear? This is the hardest exploit in the class, so. But hopefully getting it wrong a lot was instructive, except for converting the wrong address. That was not helpful. Like the other stuff should be helpful. And putting those X's at the end to shift to get the alignment right is often key. I didn't have to do it here, it just worked. But any questions? In all its glory. That one works. It'll be something different for level 12. But. Okay, I don't see any reason to continue on today. We only have 3 minutes, so. It's Vish or Lawrence or Teo. You know, Teos has a stomach flu, he said. Okay, go forth, go on. See you on Thursday. We'll finish this up.